Hola a todos, mi nombre es José, soy estudiante de doctorado en física y este video va a ser un poco distinto porque lo que quiero hacer es compartir con ustedes una presentación que hice para el grupo de gravitación. Y bueno, la presentación es hablar un poco del polinomial affine gravity y cómo podemos acoplar un campo escalar a este modelo para generar inflación. Entonces ese es el tema de la presentación y bueno, una de las cosas que pasó en la presentación es que me hicieron una pregunta y yo no pude responder. No sabía la respuesta. ¿Ya? Y bueno, en el momento no la supe, pero típico, terminó la presentación, pasaron 5 minutos y fue como... a esto se refería. Y bueno, quiero compartir esto con ustedes como para que sepan que también, bueno, uno comete estos errores y la verdad es que no pasa nada, es parte del proceso y es muy normal y natural que estas cosas pasen, ¿ya? Así que eso, los dejo con la presentación y nos vemos en el siguiente video la próxima semana. Chao.
Yes, hello. Yes, I'm ready. Can you hear me?
Yes, perfectly. Okay. So our next speaker is Jose Peliguero, who is a student from this university, but is right now in Chile. And if you can share your screen.
Okay.
So he's going to speak about.
Let me know if you can.
Yes, we can see.
Okay, how can I zoom maybe? Oh no, that's... Okay. Wait. Stop and let me share again. And I think now it is full screen now.
Yes, much better. So he's going to speak about gravity and applications of technology.
Okay, so I'll start. Okay, thank you so much for the opportunity to share with you what I've been working on my first year as a PhD student. And the aim of this talk is to give you a brief overview on what is this polynomial affine gravity model and how we can couple a scalar field without the use of a metric tensor in this type of affine gravity. Okay, so that's the key point of this presentation. And well, this is the basic structure of the presentation. So let's start from the beginning. So what is polynomial affine gravity? It is an alternative gravitational model where the fundamental field it is the affine connection instead of the metric tensor. And therefore, the gravitational interactions are mediated by the affine connection. Okay? And also, we want to build an action only using the fundamental fields coming from the affine connection. Okay? And in its formulation, we want to exclude completely what is the use of the metric tensor. So in that sense, this is a purely affine model of gravity, okay? And I do want to emphasize that this is a purely affine model of gravity because we do not want to use the metric tensor at all when we build the model, okay? So no metric tensor here. This is purely affine. Okay, so how can we build the model? Well, to build the model, we need some fundamental building blocks. And how we can get those? What we do is that we take the affine connection and we decompose into the symmetric and antisymmetric part. The symmetric part allow us to define the covariant derivative, whereas the antisymmetric part defines the torsion tensor. Okay, and the torsion tensor we decompose again into the A and B field. The B field, it is the traceless part of the torsion, whereas the A field, it is the trace of the torsion, it is the vectorial part. Okay? And also, it is a good practice to preserve the invariance under diffeomorphisms, which is why the symmetric part of the affine connection goes to the action indirectly through the covariant derivative. Okay? And finally, we need some sort of volume to define the action. And because we do not want to use the metric tensor, what we do is that we use the wedge product. and the wedge product does not require the existence of a metric tensor. So in this model, the fundamental fields are the A and B field coming from the antisymmetric part of the affine connection, the covariant derivative coming from the symmetric part of the connection, and the volume form defined by the wedge product. Okay. And now that we have the building blocks, how can we build the action? And to build the action, what we do is that we use a sort of the dimensional analysis technique. And to do that, we define two operators, the N and the W operator. The N operator counts the number of free index of any object, and the W operator counts the weight of the object. Okay, so the N counts the number of free index, and for every upper index, it is a +1, and for every lower index, it is a -1. So when we apply the N operator to the volume form, because we are working on 4 dimensions, we get a +4. Okay, and the only object that has a weight here, it is the volume form, which has a weight of 1. Okay. So now how can we build it? How can we develop a systematic way to build the action? What we do is that we take an arbitrary term, which will necessarily be defined in terms of power law of the fundamental fields. Okay, and what I mean by that is that a generic term will have necessarily m times the A field, n times the B field, P times the covariant derivative, and Q times the volume form. And what we do is that we apply the N and the W operator to this generic term. Okay, and once we do that, we get this result. We get this and this one. And now comes the key part. Because we want to build an action, the number of free index that the action must have must be equal to 0, because we want to build scalar densities. So when we apply the N operator to the generic term, this must be equal to 0, meaning that we cannot have any free index. And because we want to work in 4 dimensions, the volume form can only appear once, so Q must be equal to 1. Okay, so Q must be equal to 1, and we're going to replace this in this equation, and then we can actually find something that we call a geometrical constraint. Okay, so this is a geometrical constraint where m plus n plus p must be equal to 4. Okay, and what it means is that all positive integer solutions to this equation are all the possible terms that can go to the action. Okay, so this is a geometrical constraint that we need to satisfy in order to build the action. In this model, we do not have the freedom to add what we want to the action. We need to always satisfy this type of constraint. And what happens is that we have 15 different types of solution. Okay, but that doesn't mean that we have 15 different types of terms. I mean, what I mean by that is that for each type of solution, we can have several types of permutation, because we need to take into account different contractions, and also we need to take into account the symmetries of the object. Okay, so we need to do a very careful analysis on each type of term, and for each term, different permutations. And this actually takes a while, but once we do that, we get the final form, and I'll present to you the action, and it is this one. Okay, so this is the action of the polynomial affine gravity in 4 dimensions. And well, it has a lot of terms because of the constraint equation that we need to satisfy. But there are some nice features about it. Okay, so first of all, it is invariant under diffeomorphisms just by construction.
Okay.
Sorry?
Can I ask you something? So the way you define the volume form, it looks to me like it's very coordinate independent.
Is coordinate independent?
No, dependent, because you just basically take the wedge products of your coordinates, right?
Yes, we are using the wedge product. Yes.
And that will be coordinate independent the way you define it. If you, for example, are using radial coordinates or Cartesian coordinates locally, that will give you a very different volume depending on where you are.
Okay. Yeah, I think there is some this dB time elevated to the alpha, beta, gamma, and delta also has a multiplicated factor that I didn't add here, but we can talk about this at the end of the. But it's something that we have taken into account. Okay.
Okay. We can discuss it.
Okay. So, where was I? Okay. Because of the absence of a metric tensor, we have this constraint equation. And because we have this constraint, a geometrical constraint equation, the number of terms that can go to the action, it is a finite one. Okay. And we call this property the rigidity of the model. Okay. So this is something that is not typically found in other modified theories of gravity, but it's something that happens here, and that is because of the absence of the metric tensor. Okay. And another nice feature about it is that all coupling constants are dimensionless, which suggests some sort, we are speculating this, of conformal invariance, and also it is power content renormalizable, which is a necessary condition, but not a sufficient condition to ensure that the model it is renormalizable. Okay, and also even though we start with a purely affine model, we only endow the manifold with an affine structure, we can still have effective metric tensors in the space of solutions. Okay, and also in the torsion free limit, we found a generalization of Einstein-Baking's field equations. So in some sense, Einstein-Baking solutions are a subspace of solutions of polynomial affine gravity. Okay, and also we can couple a scalar field to the model without the use of a metric tensor, which is something that I'll show you later. Okay, so we have the model, and now what we need to do is to find the field equations of the model. And to find the field equations, well, we vary the action with respect to the fundamental fields. And the first variation is the variation with respect to the symmetric part of the affine connection. And this is the set of field equations. And what you do here is that you have the coupling constant times the term plus the second coupling constant times the second term, and so on, so forth. And you add them all together, and those must be equal to 0. And this is the first set of field equations. Then you have to vary again the action with respect to the B field. And of course, the field equations are even more complicated. And this is something that took us a while to do because we did it by hand. And then we use Cadabra to perform the computation. So this is the set of field equations for the B field. And this is the set of equation for the A field. Okay, so we have the affine model of gravity, we have the field equations, and what we want to do now is that we want to do cosmology. Okay, so how can we do cosmology? Well, we need to build an answer for the affine connection that is compatible with the symmetries of the cosmological principle, okay, with our isotropy and homogeneity. And what we do is that we compute the Lie derivative of the affine connection along the Killing vectors to generate the symmetries of isotropy and homogeneity, which are rotation and translations. And as you can see here, there is a last term that appears because the affine connection does not transform as a tensor. Okay. So what we do is that we take the affine connection, compute the Lie derivative along those Killing vectors, and what we found is that the symmetric part of the affine connection depends on 3 time-dependent functions, okay? But we can actually banish the first coefficients under a time parameterization. So in reality, the symmetric part of the connection only depends on 2 time-dependent functions, okay? And then we repeat the same idea for the B field. We computed its Lie derivative along those Killing vectors, and we found that the B field only depends on 1 time-dependent function. And then again, for the A field, we compute the Lie derivative, and we found that it only depends on 1 time-dependent function. So the final form of the accent of the affine answer is that the symmetric part of the connection depends on 2 time-dependent function, and then the symmetric part depends on 2 time-dependent functions. Okay, so we have the action, we have the field equations, and now we have the answer. And what we do now is that we take the answer and we plug it into the field equations. And once we do that, we get the set of field equations that are this one. These are 5 differential equations, highly nonlinear second order differential equations that we need to solve. To our surprise, we can actually find an analytical solution to this set of field equations without any assumption at all. And of course, I'm not going to the details on how you can do that, but the basic idea is that the first equation has a structure like something times c, and the second equation tells us another something times c. Okay, so that tell us right away that we have 4 different branches, and we can solve each branch. And the most important branch, which has the most information, actually has an analytical solution, and the solution is this one. And as you can see here, C and eta are related to the torsion tensor, and H and G are related to the symmetric part to the affine connection. And basically the solution is something like a power law solution. Okay, so it is a power law solution in the time coordinate. And alpha, beta, and gamma are just a combination of the coupling constant. Okay, so we have the model, we have the field equations, we have the solution to the field equation. How we can get some physics from this? The idea we have so far is that we can build effective metrics in the space of solutions. Okay, that's the idea we have so far. And how can we get the effective metrics? Well, we postulate 2 types of metrics. The first one coming from the contraction of the Riemann tensor, which is the Ricci tensor. And the Ricci tensor comes from the symmetric part of the affine connection. And the second metric tensor comes from the product of 2 torsion tensors, which is the antisymmetric part of the affine connection. And this is known as the Poplawski metric tensor. So basically, we postulate that we have these 2 effective metrics, and in the space of solutions, we will know if we can actually interpret those metrics as an effective metric. And one of the conditions that we need to make sure to use them as a metric tensor is that they must not be degenerate, meaning that we must be able to invert this metric tensor. So what we do is that we take the solution and we plug the solution into the Ricci tensor, into the Poplaski tensor. And what we found is that the Poplaski tensor, it is a degenerate object, so it cannot be interpreted as a metric tensor, whereas the Ricci tensor works just fine. So once we have the Ricci tensor, which can be interpreted as an effective metric tensor, that leads us to a scale factor. And the scale factor coming from the Ricci tensor describe the de Sitter and anti-de Sitter type of space solution. We also know that the cosmological constant appears as an integration constant, and we found a solution that it is something like a combination of the de Sitter and anti-de Sitter solution, but in the limit, asymptotically, tends to be a de Sitter type of solution. Okay, so this is a purely affine model in vacuum. Okay, we haven't add any type of matter or scalar field to this model. So the next part is to couple a scalar field to the model. Okay, and how can we do that? Well, we can do that by using the same dimensional analysis technique. And instead of building scalar densities, what we do is that we build inverse tensor densities with two upper index, meaning that instead of applying n to the generic term must be equal to 0, or now n must be equal to 2. And now we have this new type of geometrical constraint equation that we need to solve, and all positive integer solutions to this equation are all the possible terms that we can couple the partial derivative of the scalar field. Okay, so this is a table that contains all possible terms to couple the partial derivatives. And well, of course, now we need to do the same analysis again, and for each type of solution, for each type of term, we have different types of permutation. And this is a little more simple than building the action, but still we need to do this carefully because we need to make sure that the two free upper index must be symmetric. And once we do that, we actually find the most generic term, which is written in 12, and the potential energy term rescale the volume form. And this is something that is done. Well, I don't know if this is the standard practice in the fine geometry, but we take an inspiration in the work of the work of Hensa, where he proposed this idea. So the final form of the scalar field action is written in 13, and as you can see here, the partial derivative are coupled to the volume form, to the B and A field, and that's how we can couple the scalar field to a purely affine model of gravity without the use of a metric tensor. And something that interesting, at least for us, is that the number of ways we can couple this, it is a finite way. It has a finite number of terms. So we cannot couple the partial derivative to whatever we want. The rigidity of the model is inherited to the scalar field action. Okay, so I think that's something really cool, at least for us. Okay, so we have the action of the polynomial affine gravity, and we have the action of the scalar field. And now we need to vary the action again and find the new set of field equations. These are the field equations for the gamma field. They are severely modified because of the presence of the potential and the scalar field. And the field equations for the A field remain the same. For the B field are also extremely modified. And also we need to vary the action with respect to the scalar field. And equation 19 will be something like an affine Klein-Gordon equation. Okay. So these are the set of field equations, and what I want to show you is we haven't found any solutions so far, but this is the current plan we are following right now. Is that first we build a model, then we find the cosmological answer, the field equations, and we solve the field equation in the framework of cosmology. Now, we couple a scalar field, we found the new set of cosmological equations, and what we are doing now is looking for analytical solutions for different types of potential. And once we found the solutions, we can build effective metrics in the space of solution and see what type of universe is described in defined geometry. And once we do that, the next chapter will be to study defined perturbation theory, which hopefully lead us to the cosmological observables. And if anyone wants to join me on this novel quest to find analytical solutions to the set of field equations, please feel free to write me or send me some help. Okay, and that's it. Thank you so much for your time.
Thank you, Jose. So any questions? Maybe Akea wants to comment something about the volume invariance.
Oh, nothing more than what I said, but
so I think that maybe there is the square root of the determinant of something, like the determinant of the symmetric part of the bits, that would make the volume invariant.
Yeah, I think
that makes it coordinate independent.
Yes, because in this form it is really dependent.
Yes. So this is in this form. Basically, you have a four-form component which equals a tensor density is 1. But the value of a tensor density is coordinate independent. So if you change the coordinates, that one will have another value.
Yeah.
But if you don't add it, then if you don't take into account that there is a tensor density there, that 91 in some coordinates, maybe the one you're using, but not in general.
But then you are restricting that action to a specific family of coordinates.
Exactly. That's exactly what is happening.
It's like a unimodular or something like that.
Yes. So yes.
Okay. Okay. So I think we need to think about this. Okay.
I do want to apologize, but I didn't understand anything because
okay.
of the question.
Was a useful discussion. Basically, that the volume element that you are using in that action is really invariant under changes of coordinates, because if you change the coordinates, you get the determinant of the change of coordinates.
Yeah.
So you need an invariant volume. So
yeah,
actually, the determinant of whatever. Using a tensor density.
So you put out the square root of the determinant of the Ricci to make the volume element invariant under coordinate changes.
Yes. Well, if we use the determinant of the Ricci tensor, in order to do that, the Ricci tensor must be well defined, and in some sense, the Ricci tensor can be interpreted as a metric tensor. And that is something that we do not want to use, but also the volume defined by the wedge product, it is also multiplied by an arbitrary function that I didn't write in the presentation.
Okay.
So this arbitrary the scalar density, the tensor density that you need, but if that function transforms in a particular way, and then coordinates it.
It is not really a scalar function. It is a density, right?
Yes.
Okay. Yeah. Well, I think it's something that we need to about the model that I don't know at the moment.
So in the end, I think that you will need to assume, apart from the connection, the existence of a volume element that is given, like people doing unimodular gravity. They assume the existence of an external volume element, and then they fix it with constraints, for example. There are several ways in which
Yeah.
you have to assume the existence of it because otherwise you can't integrate.
Okay. Okay. Yeah.
Okay, any other question or comment in the audience here or there?
I have a question.
Maren?
Okay.
Yes.
Oh, okay. Renan, please go ahead.
Okay. There is something that intrigues me in these purely affine frameworks. Do you have to modify the equivalence principle in some way? Because, of course, you have a connection. Then you have the autoparallel curves of the connection, and it describes the free-falling observers and those things. But, I mean, you don't have a metric. So, in principle, you don't have a metric in principle, then I don't know exactly how is the Einstein equivalence principle in this way, in this framework.
Yeah, well, it isn't obvious to us that there is an equivalent principle at the moment, but I think in previous work there is a proof on how you can recover that result, but it's something that I haven't done by myself at the moment, so I couldn't answer that right now.
Okay, thank you.
Okay, so Amare, maybe you want?
The dynamical and the dimensional analysis, was there any particular reason why you chose the integral values of your MN, PQ exponents? Would it not be say that the product of those quantities would give you a defined dimension, but individual exponents would be fractional? Is that not a possibility?
So why are you considering integer indices for the dimensional analysis? Is it possible to have fractional numbers?
Okay,
Yes.
so yeah, I'm sorry, if we consider.
Yeah, the numbers that you have in that table are all integer. So
Yes.
have fractional numbers?
No. I don't think you can use fractional numbers. No. I think this works only for integers numbers. I don't know. I have never heard of taking the square root of a tensor. I don't know if that's where your question is.
That's more or less like that, yeah.
Yeah, no, I'm not so sure if we can take fractional numbers, because in that case, if we could potentially take fractional numbers, then the action has an infinite number of terms.
Exactly my point, yeah.
Yeah. Well, I think it's something that I will talk to with the group about it. Yeah.
The problem there is that you would like because these numbers are related to the indices of the tensor somehow, right?
Yeah.
So this is like, I don't know if you know the nature of T going to 4 Einstein argument thing, but they were kind of doing a similar thing. They were saying that they were doing this with the dimensions. The problem is that the components of tensors are not well defined.
Okay. Well,
the dimension, as far as I know, I don't know if there is a formulation for manifolds with arbitrary real dimension in which you can define a tangent space and you can define the dimension of it. But the end.
Okay. Well, this is very similar to what does in the first order formalism, when you use the field bank and what else, and the field bank and the spin connection to build every possible contraction by and also setting the torsion equal to 0. It is something kind of like that.
Yeah. Thanks.
Okay, then let's thank Jose again.
Okay, thank you.
Next speaker.